Hello, welcome to Basics of Finite Element Analysis. Today is the second last day of this week, that is the 7th week, and in today's lecture, tomorrow's lecture, and maybe in the third lecture also, we will discuss eigenvalue problems, what they mean, how they are formulated, and how are they analyzed. So, that's going to be our focus, eigenvalue problems. Now, this term eigen, it comes from German, and it is also there in Dutch language. And it has several meanings, but they are all related. First meaning is own. Okay. Second meaning is unique. Another interpretation is characteristic. Another interpretation is peculiar or self. So, these are the ideas which, when a German speaks this term eigen, they come to his mind: own, self, unique, characteristic, peculiar. In context of mechanical engineering problems or any problem for them, mathematical problems, we say that a system has an eigenvalue. It means that there may be some number which is peculiar, or it is a characteristic of that system. So, it will not depend on some external force, but it is independent of some external force, because if I am putting some force on the system, then that number may change, but there may be some number or some property of that system which is unique about itself, which is its identity. Another interpretation of eigen is identity. So, I will give you an example. First example. So, I have a spring, mass, and I apply a force, and let us say I apply a harmonic force E I omega t. Okay. Now, when I am exciting it with this force, when I am exciting this system with this force whose frequency is omega, then the system will get excited at the same frequency omega. So, this omega is not a characteristic of the system. Okay. But suppose I remove this force. So, K is when F naught is equal to 0, and then if I disturb this mass by a little amount, then the system will vibrate back and forth at a unique frequency. Let us call that unique frequency as omega. That unique frequency will depend on mass, stiffness, and the boundary condition of the system, and that unique frequency will be called eigenvalue, and eigenvalue is one word of the system. So, it does not depend on an external factor, it depends on everything which is internal to the system. And what are the things internal to the system? Boundary conditions, and in this case stiffness and the mass. In another system it may be something different, but some things which are unique about and internal to the system. So, eigenvalues are related to something internal, things related to system. Another example. So, before I go to another example, here the governing equation is mx double dot plus kx is equal to f naught e I omega t. Okay. And if f naught is equal to 0, if f naught equals 0, then my equation becomes mx double dot plus kx equals 0, or I can express it as x double dot equals minus k over m times x, or I can write this as a function of x, which is the right side, equals some constant lambda, and this lambda may be an eigenvalue. So, if before I use that, times another function of x, which is bx. So, if I can express, so if there is a system which does not have, which is not seeing any external force, and if I can represent that system as in this form, Ax is equal to lambda times Bx, then lambda, so A will depend only on the internals of the system, there is no external force in the system. B also depends only on the internals of the system. So, and these two sides will be equal if there is appropriate value of lambda. So, this lambda is known as eigenvalue of the system. So, this is eigenvalue of the system. So, this is a very general statement for one dimensional eigenvalue problems. Okay, this is a very general statement. We will see another example. Axial motion of bar. Okay. So, you have the governing equation is rho a second derivative of displacement. So, u is the displacement, not velocity. So, rho a times acceleration of a particle minus E a du over dx, and I am differentiating this whole thing with respect to x. And on the right side I have the external force. So, how is this? Suppose this is a bar, this small element of the bar, maybe there is some q. So, this q could be a function of x and t. This is my area of cross section. E is the Young's modulus, rho is the density. So, the axial motion of this bar is governed by this differential equation. If I have to find the eigenvalue of the system, what should I do? I should make q to be 0 and then solve the equation. Then the solution will give me the eigenvalues of the system, because when I am solving it using q, it is not, everything is not internal to the system, right. So, when I am doing eigenvalue of the, then, so for EV, first thing I do is q, I remove q. So, I set q to be 0. So, rho a u dot dot minus E a u dash, and then again I differentiate, this is equal to 0. And if I mathematically process or manipulate this equation, I can again express this equation as a, so as a function of, so a which is a function of u is equal to some number times another function of u. I can express this as like this. Okay. So, this is, so I am again able to So, this is my eigenvalue formulation of the system. So, this is again same format which we saw earlier. How do we get there? We will actually see it, but I can express it in this form. I will do another example. So, the other thing I wanted to mention is that eigenvalues are not always about vibrational frequencies, but they reflect something internal and unique about the system. We will see one example where they are not the frequencies of the system, but right now we will discuss beam vibrations. Okay. So, for a beam which has a cross section A and a moment of inertia I and Young's modulus E and density is rho, the governing differential equation, the dynamical equation is d rho A W dot dot, second derivative of W. So, W is deflection plus E I W prime prime equals F. F is the distributed force on the beam. Again, if I have to find the eigenvalue of this system, the first step I have to do is I have to equate F to be 0. So, for eigenvalue calculation Fx, we make it 0. So, my equation is reduced to rho A W prime prime plus E I W rho A times second derivative of W plus E I W prime prime, the entire thing differentiated twice in x, this equals 0. Okay. And again by mathematical manipulation, I can express this thing as in this form. How do I do it? I can consider W as a function of t and x. I can separate the variables and I do all the mathematics, I can express it in this form by variable separable method. I can use the same variable separable method and I can get it here also. Okay. So, that is not a problem. So, in all these examples, this example spring mass system, axial motion of the bar and beam vibrations, it turns out that lambda represents the angular frequency, square of angular frequency. Okay. That is what it turns out. But now we will consider a case where that is not the case, where it is different. So, here we will discuss buckling of a beam bar. What is it? So, I have a bar and I am applying some force, and if I keep on pressing the bar, initially the bar will just get compressed in the axial direction, but once the force exceeds a particular threshold, the bar will do this. So, it will buckle when the compressive force P exceeds a particular number. That particular number depends on the characteristic of the system, it does not depend on P. So, this is one case where the eigenvalue is not related to the angular frequency of the system, but something different. So, for this case, the governing equation is E I W prime prime plus P W prime prime equals 0, or in this case this is very straightforward, E I W differentiated twice and the whole thing is differentiated twice is equal to minus P W prime prime. Now, here we directly see that this is nothing but of the form A of U, A of W is equal to lambda of W. It is of that form. So, this is again an eigenvalue problem, lambda B of W. So, this is one example where the eigenvalue is not related to the natural frequency of the system. It is a different thing. Here eigenvalue corresponds to the buckling load of the system. And a last case is for heat conduction. In a bar. So, here if I have a bar with cross sectional area A, then the governing equation is rho C A dtu du over dt. So, here U is equal to temperature in this case, okay, and this minus K A d, okay. So, I have to make a small correction, it is now partial and same thing here del u over del x and the entire thing is differentiated with respect to x and this equals heat which is generated internally to the system per unit volume. So, this is the differential equation. Now, in this case also if I have to compute the eigenvalue, this is the thing which is the q is the term which is external to the system, right. So, if q is equal to 0, then solution of this differential equation will give us eigenvalue, okay. It will give us the eigenvalue of the problem. And again in this case also if we do this variable separable method, we will be able to express the overall equation as A of u equals lambda of B of u, this form. So, in a sense a quick summary of this thing is that when we are talking about eigenvalues, we are talking about finding some numbers which are specific to a particular system and they can depend on the material properties of the system, they can depend on the geometry of the system and they will depend on the boundary conditions of the system. What they will not depend is on any other external factor which could be a force or a heat source or an excitation or whatever, okay. So, that is the overview of eigenvalue problems. Next what we will do is we will actually solve a particular eigenvalue problem and that is for the vibrations in a bar, that is what we will solve and that is going to be the focus of ours for tomorrow's lecture. So, today what we have done is we have explained what an eigenvalue problem is and tomorrow we will actually solve one of these eigenvalue problems using the finite element method. So, that concludes our discussion for today and we will meet tomorrow.